Okay, now let's do two applications of this diagonalization. So, powers of a matrix and exponential. Let's begin. Power of a matrix, if you want to square your matrix, obviously you're just going to multiply A by itself. Now assume that A is diagonalizable. It's just going to be P d P minus 1 times P d P minus 1. See what's happening? This is just going to create identity, and then you get d squared. So you get P d squared P minus 1. Interesting thing with diagonal matrices is that, well, let's take a simple 2 by 2 matrix. The square of a diagonal matrix, do you see what it's going to give you? Well, it's just going to give you d1 square 0 d2 square. So the powers of a diagonal matrix are extremely easy to compute. If you've got generality d1 up to dn as your diagonal matrix, the power k of this is just going to be d1 power k, d2 power k, etc. up to dn power k, and the zeros will remain 0, and that's it. All right? So now you can also extend on that side that formula if you want to compute a power k. That's just going to be p d p minus 1 p d p minus 1 k times, and every time you have the p minus 1 with the p collapsing into an identity, well, it's just the identity matrix, so identity times d is just d, and so on. So what remains is going to be p d power k p minus 1, and that's something very, very easy to compute. All right? So that's very important. Then we would see some use of this formula. And we can also compute the exponential of a matrix. Let's see. So exponential E of A, also assuming A is diagonalizable. So for this, well, you learned last year that you could do the Taylor expansion of the exponential of x function. If you remember, that's just 1 plus x2 over 2 factorial plus x3 over 3 factorial plus xn over n factorial plus some small o. Thing is that what we're going to learn, and the important idea was that this expansion was local because that was a small o of xn, all right? And so x had to be small or close to 0 in order for this to converge. What we're going to learn, actually, that's going to be first chapter of second semester, is that this expansion, you can write it as a series, and that's going to be the series expansion of the exponential from 0 to infinity of x power, so let's take an exponent, an index n, so that's x. N is equal to 0 up to infinity of x power n over n factorial, right? So for 0, you just get 1. For n is equal to 1, you get x, n is equal to x2 over 2 factorial, etc. Right? What we will learn is that this is actually true everywhere. So this way, we will also define my exponential of a as the infinite series of, well, maybe I shouldn't choose n, p equals to 0 to infinity of x power p divided by, of a power p, because we've already defined a power p divided by p factorial, okay? And we know that the a power p are all going to be p d power p p minus 1 divided by p factorial. Okay, and by linearity, I can really write this p sum of d power p divided by p factorial p minus 1. Oh, I've got too many p's, but well, anyway, that's a small one, that's a big one, right? And so I've got my sum of my diagonal matrix to the power p divided by p factorials, and that's just going to be this thing. Well, on the diagonal, that's just going to be sum of diagonal matrix is just going to be diagonal, and then the diagonal, you're going to get expansions like this, all right, so you're going to get exactly exponential of d. That would be exponential of d, and the exponential of my diagonal matrix is just going to be exponential of d1, exponential of d2, exponential of dn. Okay, and so the exponential of the matrix is just going to be e. Then I get e of lambda 1, e of lambda 2, if those are the eigenvalues of my matrix A, times p minus 1. Okay, so we have just defined a new interesting stuff, exponential of a matrix. All right, next huge application, right? Homogeneous first-order linear differential system. What do we mean by this way? We mean something that, so you know what differential equation, linear differential equation of the first order is. It's something, let me write it with x of t is equal, x prime of t is equal to, let's say, a times x of t. That's homogeneous because I don't add any source term. I only, if I added some f of t, that would be a source term. So I don't have anything. I only have terms depending on my unknown function x. And it's linear and constant coefficient. All right. Now let's say that I want two unknowns, x1 and x2 of t. Let's write this. Sorry, so maybe let's call that a1 and let's call that a2 x2 of t. Right? If this is what your system looks like, it's very easy to solve because the two equations are actually independent, right? So how would you solve them? You just write x1 prime over x1 is equal to a1, and then you do the usual solving for that. So you know that we're going to integrate. So on one side, I get the log of x1 of t. On the other side, I get a1 times t plus integration constant. Then we apply the exponential on both sides. And on this side, I get x1 of t is equal to that exponential of k. If k is an arbitrary constant, it's just going to be another arbitrary constant, plus the fact that I should put some I should put some absolute values around my x1, but as k can be an arbitrary constant, I can also choose the sign of this arbitrary constant that depended on the fact that we know x is not going to cancel. So I know it's going to be only positive or negative. So this being said, that the solution is this one, a1 of t. Very easy. All right. So well, that's something we will work on that again, but that's the simplest equation you can hope for, and that's the solution you get, right? So we get two solutions. X1 of t is some arbitrary constant. Well, let's note that k1 to be consistent with these notations. E of a1t and x2 of t is k2 e of a2t, right? But this is very simple to solve, and I can solve the two equations independently. But now what's happening when your two equations are not independent? Let's say you've got x1 of t prime, x2 of t prime, and that's just going to be well, let's call them a, b, c. I'm getting lost in my indices. A x1 of t plus b x2 of t. And this one is going to be c x1 of t plus d x2 of t. Okay, what can I do now? I can't solve them independently because they depend on the other one, right? But what I can do is to write the matrix way that we have this system. That system is just going to be x prime is equal to my matrix A, B, C, D times X, where X is actually a function of T, is X1 of T, X2 of T. Okay, so this is the system that I have to solve. I've got to solve something like X prime is equal to A times X with A some square matrix. Thing is that if A is diagonalizable, so if A can be written as P, D, P minus 1, this is going to be simple to solve. All right, because I will be able to write a diagonal, a system where the two equations won't depend on each other, because I would have a diagonal matrix with, a diagonal matrix with only coefficients, non-zero coefficients here, which would make the two equations independent from each other, right? So let's try this. X prime is A, so P, D, P minus 1 times X. All right, let's multiply both sides of this equation by P minus 1 on the left. So I get P minus 1 here, P minus 1 here, okay? Right, so what do I get? First thing that I get is that those two P minus 1 times P, that's just the identity, so that's neutral element, so I can just rewrite this as D P minus 1 times X and P minus 1 times X prime. Good thing is, observe that we have P minus 1 X, P minus 1 X prime. Let's put a new variable, so a substitution. Let's put Y is equal to P minus 1 times X, okay? So Y prime is just going to P minus 1 times X prime, because P minus 1 doesn't depend on T. The only thing that depends on T here is the X. Right, so what we have is, if I use my Y variable, here I've got Y, here I've got Y prime. Y prime is equal to dy. Okay, excellent. So that gives me a diagonal system with, well, n equations that are going to be independent of each other, right? So let's assume I've got my two, I was with my two ABCD matrix, and that I've got lambda 1, lambda 2, 0, 0 as my D equation. And so we know that Y prime is equal to lambda 1, lambda 2, Y. So I get very easily that Y1 of T is going to be arbitrary constant E of lambda 1 T, Y2 of T, arbitrary constants E lambda 2T. All right, but then I need to go back to my original variable. I had, don't forget, I had this one. Y is equal to P minus times X. So now that I've got Y, how can I find X? Well, just invert this formula. It gives me that X is equal to P times Y, right? So X is just going to be given by my matrix P times this vector K1 E lambda 1T, K2 E lambda 2T. Okay, and that's it, I've got X. The other good news is that we can even write it in a nicer way. We know that P is the matrix that contains the eigenvectors. So my example is with 2 dimensions. So 2 eigenvectors, let's say this is V1 and this is V2 in my columns. So if I rewrite this as V1 column, V2 column times this vector, K E lambda 1T, K E lambda 2T, well, different case. I can also write this as K1 E lambda 1T times my vector V1 plus K2 E lambda 2T times my vector V2. Okay, so what do I get? I get that my solution is actually a linear combination of my two, sorry, I forgot the T here, of my two eigenvectors. Okay, so that was quick because I didn't want to make much longer videos, but we're going to work on that, don't worry. All right, thank you very much.